Hi class, so now that we've learned about how to deal with the view frustum and how to call things or clip things outside the frustum and all the ways we can accelerate that, let's move down the pipeline. We've already transformed our geometry, we haven't called it yet, and we've transformed it down, but we haven't drawn it yet. So we have another chance to fix this, to call and to save work. And this is called clip space culling. Okay? And here's the idea. So it's actually not in 2D, it's actually pretty easy, right? In 2D, it's easy to check for clipping and culling. Because, and the reason it's easy in 2D is we have this really nice, simple defined view volume in our coordinate system, right? And there's objects in and out, and we can simply just check x and y against the bounds, right? It's easy. Just check against x, y bounds. And if our box is axis aligned, it's really simple. If it is rotated, if our camera is rotated, that's okay. We figured this out. We can on-rotate it by working in camera space. Right? If we work in camera space, bam, done. Things are on-rotated, and we can use these axis aligned. So it's really simple. Can we do something this simple in 3D? And the answer is yes. And the way that it works in 3D is we take this idea where I have just a simple box, this really simple bound, none of this frustum and like view volume looking off in some random direction business, a simple shape. We can get that by working in NDC, working in normalized device coordinates. Now remember that the way this works is if I have a point, in model space, I multiply it by the model to get it into world space. I multiply it by the view, that's my camera, to get it in camera space. And then I project it into normalized device coordinates. And then I use my viewport transform. So I can actually work here. After I've projected it into normalized device coordinates, then I can start my culling in there. Now remember, normalized device coordinates, they go from -1 to 1 in each dimension. Right? The whole idea here is no matter what your projection is, even if it's like, one of these perspective view volumes, after you convert it to normalized device coordinates, you get this really well behaved cube. It collapses in straight, it turns it to almost like an orthographic after it does the adjustments that go from -1 to 1, -1 to 1 in every dimension. So, right, we get this nice 1 by 1 by 1 cube. So then if we have that cube, we can take advantage of that. It's really a simple calculation then. If -1 is less than or equal to x in my normalized device coordinate, and that's less than or equal to 1, and -1 is less than or equal to y in normalized device coordinates, which is less than or equal to 1, and like that, z. So if my x and my y and my z are within that range, then my point is within my view frustum, within my view volume. Okay, so this is my left to right, this is my top and bottom, and this is my near and far. Okay, now remembering that the perspective has already been taking account for here. This is post-perspective correction. So this works. It's really simple to program. You have a couple if statements. You can do it in hardware. It's an easy check. It's all normal. But it's not without its faults. There are some problems here. First of all, each vertex, it does have to be transformed. before we can do this check, right? Each vertex does have to be transformed. So if we can, we should be culling earlier, using some of the other methods we talked about. In fact, we're going to learn about more methods shortly, other methods which will help us cull even more earlier. So each vertex does have to be transformed. The other problem here is each vertex requires 3 divisions. And they're very expensive. Remember, to get this normalized device coordinate, to get these, we have to divide by that z if we're in perspective, right? We have to, boom, divide that to bring that in. And divisions are really expensive. Why do we need to do all these 3 if we're just going to delete the point anyway? Okay. This is in perspective projections. Okay. So there's actually a better way to do it. Let me spell out as a reminder, first of all, where we are. So up here, up here, when we're doing this projection, if we stop in the middle of the projection, okay, we have this, if we stop in the middle of the projection, then the perspective gives us this homogeneous coordinate. Right? It actually doesn't do the division for us. We have to do that after to normalize our homogeneous coordinates. So let me spell that out. Gives us a homogeneous result, right? The actual output from the perspective matrix is x, and I'm going to put h for homogeneous coordinates. Actually, I'll spell that out. Let's put homogeneous coordinates, okay? So it'll give us x in homogeneous, it gives us y and z all in homogeneous, and w, okay? Now we know that before we can use it in our normal space, our standard coordinate system, we have to convert it, and we do that by dividing by, not by z, we divide it by w, right? And then yh is divided by wh, zh is divided by wh, and the same thing the bottom goes to 1, right? So we need 3 divisions here. The bottom one we can just put the one without doing the division. And that gives us our x in NDC, our y in NDC, our z in NDC. Okay, those are equal. So if we could somehow, here's the idea. Can we check these bounds before the division? How would that work? Right? If we can, this would save a lot of work. We'd save a bunch of divisions in every vertex that we cut. Okay, so this would actually save a lot of work. Ooh. So, yep, we can do it. And this is actually what we call clip space. And when you hear people refer to, oh, just do that in clip space, what they actually mean is this spot right here before you do the division. I'm going to write this out again. This is my projection, my point in model space times by the model, view, projection, and then viewport. If we, right at the end of the projection matrix, before we correct, before we divide, so after applying the projection matrix, but before completing division, when we have those homogeneous coordinates, this is called clip space. Okay. So that's an example of a clip space coordinate before we do that. After projection, before we do that division. So we can actually work in clip space to do our culling if we want to. Now remember, previously we said we'll test if -1 is less than or equal to x in DC. I'll copy this out again. System 1, -1 less than or equal to y in NDC, less than or equal to 1. And these are the bounds that I'm checking. Right, this is what my goal is. We've already agreed that this is a good way to cut my call my points. Now I'm going to rewrite this. So right up above here, I just said that these are equal, right? X in NDC is the same as x in homogeneous divided by w by inhomogeneous. That's exactly how we do it. So I'm going to update my math here and rewrite this. So instead of x in NDC now, I have x of h over wh, right? So they're equal, okay? Less than or equal to 1, less than 1. And I'll do the same thing for y of h over wh. They're all equal, so I can do that. Now, here's the trick. Really simple. I'm going to apply everything by wh. Remember, you can do that as an equation. If you multiply both sides, or in this case all three sides, by the same amount, nothing changes. So this gives me the following. This gives me, so negative wh, because I'm multiplying it there, less than or equal to x of h divided by w of h times w of h is just my x and my homogeneous coordinate. And on the right, it's wh. Same thing for y. So all that we have to do now, we can avoid that division to do our check. We compare, all that we do is we compare the x against the w, the y against the w, and the z against the w. No division necessary, and then call. And for the points that are kept, then we can do our expensive division. So we check, oops, x of h, y of h, z of h, against w of h, and call before we divide. Now, yeah, and then if, for example, if all 3 points in a triangle miss, we call the whole triangle. We save a lot of work just for a couple of comparisons, right? And then we don't have to do divisions, we don't have to do rasterization, we don't have to do z checks. All that stuff goes away for each triangle. Now, this idea here of clip space culling, this is pretty standard. This is really standard. You'll read about it in a lot of places. OpenGL does it. It's built into your rendering pipeline, basically. It's built in. And if you're building your own engine, kind of like an earlier assignment, then you can also do this if you wanted to. If you're doing a 3D projection, to just call those points before doing all of that work. Okay, so that's what clip space culling is. It's a really clever trick where we stop after projecting. I'm going to highlight this. After projecting, but before doing the division, then we check whether within the bounds of our view volume or not, and we can call before division and before rasterization. Great.